March 1st, 2022, electric field experiment with concentric electrodes. So what we're going to do today, we're going to map the electric field of two concentric electrodes, like this configuration that you see here. Okay? So the equipment for this lab is one power supply, one power cable for the power supply, two black cables with banana termination, one red cable with banana termination, one red probe. Probe has a very sharp end, so please do not punch a hole in my resistive paper that's going to be given to you. Okay, cork board, 6 pins, one ruler, one resistive paper with two concentric circle electrodes, digital multimeter, and two alligator clips. That's the equipment that we're going to use, and the procedure is, here you go. You start with resistive paper, you get the resistive paper, and you place the resistive paper on the top of the cork board. You insert 4 pins to the edges of the paper to secure the paper on the cork board. You put another pin on the outer electrode, anywhere along the outer electrode. Just make sure that the surface contact, the surface of the pin is in full contact with the electrode. Okay, the surface, the lower surface of the pin cannot be displaced out like that, okay? Otherwise you're not gonna get a good result. You want to have the whole surface of the pin laying down there in contact with the electrode. So place another electrode, another pin at the middle of the paper. Again, you want to have the full surface of the pin contacting the electrode. It shouldn't be half in the electrode and half in the paper. Turn on the power supply and set it to 10 volts. Leave it there for the remainder of the experiment. Connect the outer electrode to the negative of the power supply using the black cable and the alligator. Remember, we have the alligator, so you can connect the alligator at the end of the cable and the alligator clip. The alligator clip is going to clip the pin, and the other end of the cable, the banana termination cable, is going to connect to the power supply. Here you go, connect the inner electrode to the positive of the battery using the red cable. So again, the moment that you connect the outer electrode to the negative of the battery, the outer electrode becomes negatively charged. The moment you connect the inner electrode to the positive of the battery, the inner electrode becomes positively charged. So again, both pins, how do we connect to the pins? You have to have the alligator clip attached to the banana cable, right? And the alligator clip clips into around the pin. Second black cable, okay, you're gonna get the second black cable connected to the black jack of the multimeter that was given to you. And the other end to the outer electrode as well. You're gonna have two black cables connected to the outer electrode. One cable is gonna go to the negative of the power supply, the other cable is gonna go to the negative of the multimeter. And finally, connect one end of the red probe to the red jack of the multimeter DMM. And leave the other end of the red probe laying down on the table. Okay, so the experiment set. Now we are going to check if everything works fine. Okay. Before doing the actual experiment, we're going to come up with some simple tests to see if the equipment is working well. What we're going to do? Okay, first what you do, you set an imaginary x-axis through the middle of the paper. Do not draw the axis on the paper. You have to visualize that in your memory. Okay, the origin of your x-axis is going to be here in the center electrode. You're going to draw a y-axis as well. Visualize that. Set an imaginary y-axis along the vertical direction. Do not draw the axis on the paper. As a check to your equipment, touch the red probe on the pin of the outer electrode. Yes?
Can you also use the continuity test mode?
What's that?
Can you also use the continuity test mode of the multimeter?
1 minute. Let me. So as a check to your equipment, touch the red probe on the pin of the outer electrode. They're supposed to read a very low voltage. Can be 0 or can be a very low number like 0.01 millivolts. Okay? Check that. You shouldn't see 1, 2, 3. If you see 1, 2, 3 half volt, there's something wrong there in your setup. Okay? So you're touching the pin. When you touch the pin, it's a far more reliable zero reading that you get. Okay? As a second check, touch the red probe on the surface of the outer electrode. Anywhere. Touch here, several places. Touch a second check, touch the red probe at several places. At several places on the surface of the outer electrode. You're supposed to read a number that's very close to 0. Okay. As a third check, touch the red probe on the pin of the inner electrode. You should read close to 10. And then touch on the electrode. We're checking out the equipment. Okay? If we flunk in any of those tests, that because there is something wrong with your setup. Those are the simplest tests that you can do to your setup. Okay, the simplest measurement that you can do is your setup. If your setup doesn't pass those 4 simple tests, that's because there is something really wrong with your setup. What we are going to do next is far more difficult than what you did now. Okay? So if you pass all those 4 checks, you should be able to start your experiment and get some good data. Let's see. It doesn't guarantee that you get it, but at least you pass this simple test, right? So here you go. Starting from the outer edge, find a 0.5 volt point along the x-axis and write its coordinates. The half volt point should be closer to the outer edge. Okay? So find this coordinate. Y is going to be 0, but x, you're going to measure with your ruler. Measuring with your ruler the x position of this point. Okay, again, when you're touching your paper with that probe, do not crease, do not punch a hole through it, or you're going to damage your whole experiment. Next, get 1 volt along the x-axis too. Okay, get 2 volts, 3 volts, 1, 2, 3, 4. Let's see, 4 volts and 5.5 volts. I've been doing this experiment for several years, so I think those values of voltage is a good one. When you get those points, don't forget, you gotta log into your spreadsheet. Let's get the spreadsheet. Here you go. The spreadsheet is right in here. I'm gonna download the spreadsheet. I'm gonna show you. Here we go. Okay, so here you go. Nope, lab number 2 in the spreadsheet. Okay, measurement. Oh, enable content. Continue. Here you go. Half volt. First measurement of half volt. Don't forget, you have to write down the voltage that you're reading in your multimeter. It's not going to be exactly half volt. You must write every significant figure that you read in your multimeter, and you're going to use the most sensitive scale. X coordinate is going to be whatever you read from your ruler. The Y coordinate is going to be 0 for this first row of points. And the same thing for the 1 volt. 1 volt, 2 volts, 3 volts, 4 volts, 5 volts and a half.
We're finding something wrong with our paper.
Okay, so let me.
The
That you're going to log the voltage value that you're reading. Okay, it's not going to be exactly half volt, it's not going to be exactly 1 volt, but should be close enough to it. It's not going to be exactly 2 volts, right? And then you got to log the x and y. The y for this first row, they are all going to be y equal to 0. Okay? So what's the next thing? We're going to do the next easiest thing. We are going now to get the points along the y-axis. Okay, after you measure all those half, 1, 2, 3, 4, 5.5 volts, we're going to do the next thing that's simpler. We're going to get the points along the y-axis, half volt along the y-axis, 1 volt along the y-axis, 2 volts along the y-axis, 3 volts, and so on. For those points, x is going to be equal to 0. And then you go ahead with your spreadsheet, measurement number 2. Log the exact value that you read from your multimeter. Don't forget, use the most sensitive scale. X value here is going to be 0. Y value is whatever you measure for half volt. 1 volt. Log what you see in your multimeter. X is going to be 0. Y value is going to be whatever you measure with your ruler.
Are we measuring from the center?
From the center, right? Let's take a look here. Here you go. See that? The axis and y-axis, that's the origin of your axis, right? That's the origin. So it's from the center, not from the edge. It's from the center. Okay? Once you are done with this second set of measurements, we are going to go for something in between. Okay? So now you're going to get 4 points, 4 additional points, a half volt. All those 1, 2, 3, 4, 5, 6, make sure all those points that you see here, they are equally spaced. Don't bunch them up in a single spot. I want them equal angles, okay? Equal angles of distance. Make sense? Okay, I'm gonna take out points if you're bunching them up in the, don't do, here you go. Do not do something like that. Like I always see. Oh, do not do something like that. And then you have this big gap, right? Between points. Do not do that. Do not do that. Here you go. I'm gonna cross that out. Do not do that. Here you go. Big cross here. Do not do that. Okay, get 4 more points that are equidistant of half throughout the first quadrant. that are equidistant, that are equidistant. Okay? Do not get them. Do not get them too close to each other with large gaps. Do not do that. Okay? That's a no-no. Every time that you do an experiment, think in terms of that. You don't want your points accumulating in a given region of your graph. So what's next? Again, going back to your data points, make sure those points are evenly spaced in terms of angle. Do not bunch up the points together like it's here, right in here, okay? Or here. That's not good experimental procedure. Okay. Next step, you're gonna get 4 more points at 1 volt. Okay, and again, just like before, get points that are evenly spaced, no big gaps between them. Note C, one very important thing, as you go towards the center, the arc here becomes shorter and shorter, right? You gotta be careful about that. You don't want get a very short arc with a bunch of points. So what do? You start invading the second quadrant. You start to get points on the second quadrant. You start at the first quadrant and you start getting points at the second quadrant as you go towards the center of the paper, of the electrode. Here you go. And that's what we get. Here you go. For 2 volts, I got 1, 2, 3, 4, 5 points on the first quadrant, and 1 point on the second quadrant. Make sure that again that this angle here is rather similar than the other angles. Again, as you go closer and closer, yeah, you have to get more points on the second quadrant, right? Here's for 3 volts. For 4 volts, I got 2 points on the second quadrant. For 5.5 volts, also I got 2 points on the second quadrant. Okay? Keep that in mind. That's what we call planning your experiment. So you can get data that looks good. Okay, as you move towards the center of the page, you were going to get arcs that are shorter and shorter. Because of that, you may need to invade the second quadrant. That's the case when you look for the 2-volt equipotential curve. Here you go. Here in this case for 2 volts, all the 6 points do not fit within the first quadrant. So you're better off choosing another point on the second quadrant. For 2 volts, for 3 volts, for 4.5, 5.5 volts, you might need to put 2 points there in the second quadrant. Next, what you should do, you're gonna plot those data points with Excel, and you're gonna draw equipotential lines, just like you did for the previous lab. Those equipotential lines should be close to that of a circle. And you're going to draw also the electric field lines that should go from the positive to the negative. The electric field lines are those red lines that you see right in here. So basically, that's how you do the experiment. Okay, here we have a sample of data, and notice that the radius for this set of points are pretty close to each other, right? Here too, it's not that doesn't deviate too much the radius, which indicates that the curve is a circle. So let's see if it looks like a circle. We are going to plot those equipotential lines. So we start with this one, x and y. Insert, chart, plot. Okay. Okay, if you want to make it look like a circle, you have to change the ratio, right? Gonna make this graph a little bit a square. Let's see, 0 to 0.08, 0.08. So we're talking about 8 centimeters. Here you go. Should be somewhat like that, right? And then if you want to see the others, you go. So what do? You click on the data points, one of the data points, right click, select data, and go for the next set of points. Here you go. Right? That's okay. So let's see. Let's do that again. I gotta move this graph from the. Okay, here you go. The next set of points is this one here. Click. Everything's highlighted. Right click. Select data. I'm going to edit this one. It's going to be half volt. 0 0.0 volts. That's the first. I'm going to add another series. The next series is going to be 1 volt. And I'm going to highlight the X position and the Y position. We should have the next set of data. Okay. Note C, right? Let's note. I'm gonna click here. Here you go. Note C that the first set of data, those two data points are too close to one another, right? That's okay, but next time just think about that, not to keep them too close to each other. But this one looks better, more evenly separated. Let's go for the remaining of the points. You go right click, select data, add another one. Next one is what? 2 volts? 2 volts. X position. Y position. Don't forget to remove this one. This one always shows up there. And now we have a third equipotential curve. Right? Let's see how it looks like. Okay, those 2 points are a little bit too close. 1, 2, 3, 4, 5, 6. Right? At this point, you're supposed to have gone to the second quadrant, right? You didn't go to the second quadrant. So now let's go to the next one. Looks like a curve, right? Looks like a circle. Select data. Add. Next one is what? 3 volts? 3 volts? Okay. X value. Let's look for the X value. X value is here. Y value. Go. Right in here. Click OK. Let's take a look at our graph. How it goes. Yeah. Yeah, again, you didn't go to the second quadrant, right? You're running out of space here as we go inside. So much that you have those 2 points that are close to one another. Next one. Here you go. 3 volts. Next one should be 4 volts. Okay. Click, highlight, right click, select data. Add, that's going to be 4 volts. X. Highlight X. Remove the number 1, highlight Y. Click. Right, and now let's go to the last one, 5.5. X. Okay, and Y. Here you go. And then we finally have our graph. Let's see how it looks like. Yeah, yeah. Again, you bunched up a bunch of points here, right? You didn't go to the second quadrant. Okay, but it's better if here you should get 2 points on the second quadrant. Wait a minute. Did you go to the second quadrant when you didn't go? You just put a point very close by there.
Yeah, towards the end, yeah.
All right. So yeah, but it looks like circles, right? Arcs of circle. So okay, once you do that, you're going to have to plot a second graph. The second graph is going to be what? The average voltage versus the average radius. Okay, so let's do that. Here you go, insert, chart, and we get something like that. Okay, you might want to 1, 2, 3, 4, 5, 6 data points. You might want to change this value here, 0.01, right? Okay, 1, 2, 3, 4, 5, 6. Yeah, good. We want to change to 0.07, right? What else you have to do? Okay, you are going to fit a curve. You need to fit 2 curves to this graph, 2 curves. Okay, first we are going to see if this curve fits the inverse of the distance, which should be the power fit. Okay, display equation on chart, display r squared. Let's take a look here at the equation. Okay, we are getting a power of x 1 minus 1.8. Okay, we usually get that approximately minus 1. Okay, but for some reason you got minus 1.8. So, and then you're going to try another power fit. Another power fit should be the log, and see which one looks better. There's a reason why we choose the log and the power fit, and the power fits. Okay, there's a reason for that. We're going to talk about that. Here you go. Didn't you didn't I don't see the right in here at the bottom. Okay, take a look what we get here. Which one fits better, the power or the log? The log fits much better because of what? Because of the value of r squared. Okay, r squared is better than this r squared here. Now, what those 2 curves represent? Okay, in general I get a number here closer to minus 1 in general. Okay, that would be, if I get something like x to minus 1, what that would mean? It would mean that would be the voltage behavior of a point charge. The electric field is 1 divided by r squared, but the voltage is 1 divided by r, okay, for the point charge. But what you see here is not that for a point charge, it's actually that for a cylinder, concentric cylinders. And concentric cylinders behave this way. The electric field of a cylinder goes, you remember how is the relation for the electric field you just derived today? Goes with the inverse of the distance r. But the electric potential is the integral of 1 over r dr, which ends up giving us a log of r. So what you have here is not the behavior of a point charge. What you have here is the behavior of a cylindrical charge. Okay, cylindrical distribution of charges. That's what we have here. Okay, so let me pause here.